That's where it starts to get nervous. I wrote it down and I got to like 0.8, and then I went to 20, or no, 20. Let's see, it's 0.875.
Okay.
Now we got 0.88, 0.878.
Oh, my buttons are not working. Welcome to Thermodynamics. I've been getting some questions about all these tables related to our properties. Some people have been looking at the homework, and yeah, there's some tricks to that, and that's one of the things about thermodynamics. One of the first hard things is like, how do we find all these properties? So that's what we're going to kind of go through today. We have these pictures of the properties, so that's nice. It gets you a sense. This picture says, you know, there's your critical point. There's the liquid side of it, and it comes down to this triple line. This is the triple point. There's your critical point. What happens here? The liquid goes, and this is probably not to scale because it comes down as a liquid, and when it gets to freezing temperature, it expands as it turns into a solid, but this expansion is only like 4%. And then it comes, so that's why that's what this thing here is about, this offset. It's the fact that liquid expands. So it isn't affected much by pressure as far as the size of it, but vapor is, and so all these numbers related to all of these points. This temperature corresponds with a certain pressure and temperature, you're going to get a volume. Or you have a certain temperature and you have a certain volume, that only happens at a certain pressure. And that relates to a certain amount of energy in each kilogram of water, if this is water. Tables, there's a surface just like this too that you could talk about for any pure substance. Carbon dioxide would have one of these. It has a triple point also. It has a critical point. It has, it may go the other way. When it freezes, it might actually shrink a little bit. That's probably more common for most things. But there's numbers that go with all this, and we have to figure out what those numbers are. So we have tables for that. We talked about that. So there are property tables in the back of your book. We're going to be looking at Appendix 1, Appendix 2. Appendix 1 is all about metric, kilograms and kilojoules. Appendix 2 is all the same data, but in terms of like BTUs per pound mass, English units. They reproduce it. They're talking about the same thing, but they're talking about it in different numbers. It's like two different languages, but you're talking about describing the same thing in two different languages, the systems of units. But a BTU is a unit of energy, a kilojoule is a unit of energy. There's so many BTUs in a kilojoule or vice versa. Pound mass and kilogram are both units of measure, and it's 1 pound mass, or no, 1 kilogram is like 2.205. 1 kilogram is 2.205 pounds mass. So there's conversions that convert between them, but they're talking about the same property, the same numbers at the same temperature, different numbers for temperature, but at a given state, you can describe it in either metric or English units. So we're looking at both for this. So there's an interesting thing. Is there no energy in ice water, for example? Is there nothing you can do to ice water to take energy out of it? Like maybe turn it into ice? That would be, you'd have to add energy to ice to turn it into ice water, right? So there's energy, and you could take way more energy out of it and take ice and cool the ice all the way down to 0 degrees Kelvin. That's really the bottom of the energy. If you go to 0 degrees Kelvin, in theory, molecular motion stops, and there's no kinetic energy in there. So our tables aren't built on that lowest number. They just say, you know, if we're dealing with steam, we're going to have a steam table. Is it likely that we're going to have any steam happening at ice water temperatures? Probably not. So for water, they'll have they'll call the saturated liquid, right, basically ice water, at 0.01 degrees C. That's just cheating for saying if it was 0 degrees C, it must be ice or mixture. If it's just a little bit above that, well, it must be water now. And when they do that, they say whatever energy it contains, there's still molecules in motion. We're going to call that 0 and build our table up from there. So if you add 1 kilojoule of energy, it will warm up 1 kilogram, some number of degrees, and we'll just go from there. So it's a reference state. And all of your tables have a reference state. If you go to the refrigerants, R134 is mostly what's most commonly used. Is the refrigerant going to go below 0 degrees? Probably so. So they have a different reference point, and they kind of take it down, and it may not be where it goes from. It may be that it goes so far down it's not useful for us to have a solid block of R134. So they'll go down to some level below which maybe the refrigeration is, you really don't want to use it below that temperature because of efficiency. And I forget it's minus 20 or minus 40, but if you look in the it's minus, oh, there we go. So they use the minus 40 reference temperature. And the interesting thing about minus 40 is it doesn't matter if you're talking about centigrade or Fahrenheit. If you look at the scales, they both are minus 40 at the same temperature. That's where those two scales cross. So you're probably not going to have a deep freeze using R134. You've got better stuff to use, but that's everything's 0. And what is 0 at that point? It's actually the internal energy, and then the work, the PD part of it. And so that means that's basically internal energy. They're calling 0. Is there still motion and energy? Yeah, there's motion and energy, but we're going to say that's what we reference as, and then everything we build up the tables up from there. Yeah, question. What is U?
Yeah, UMass.
Okay, that's internal energy, and S is entropy, which you really haven't talked about, but so this is that's what they build everything up from. And really, this one is yeah, it's all about the internal energy, which we don't really care about. But if we look at the tables, which we'll do now, and there's a bunch of properties. Okay. I don't want to hear that. Try opening it again.
So just to make sure in the meantime, the one that is on syllabus right now, it is the correct revision?
Yes.
It is, because I remember you looking and saw a couple of discrepancies, but it is the final one.
It's final one at this point.
Okay.
It's correct now.
Okay.
If something happens, an asteroid hits the room and we have to cancel class for 3 days, I might have to do something different with
That's
it.
good.
Now, I'd like to know, it's not, well, let's see if it likes the other one. Oh, joy. Okay, never mind that. This is why they made books. So table A4 is the one for zoom it up a little bit more. And if you brought along your book, you can follow along. But you'll notice there's the temperature, 0.01 degrees C, can't be ice if it's above 0. And you come over here and saturated liquid, that'd be liquid that's you give it any more energy, it's going to turn into, at that pressure, that's our saturation pressure at that temperature. And at that value, that's our 0 state. And then over here, they also say, well, we're going to start here with our entropy and then build up from there. Enthalpy is really what we're going to use almost all the time. And it says 0.001. What's going on there? Remember what enthalpy was defined?
Is it the release?
Say again?
Is it the release?
It's the
release of power?
no, yes, it's all the enthalpy is internal energy, the molecular motion plus pressure times volume, work. In order to get, if you take this pressure times that volume and add that to internal energy, you end up with that value. 0.001 times 0.6 would be 0.0006. But if you round it up to 3 digits, you get 0.001. So they just really, where this comes from is they take that value, multiply these two, and add it. And for the next one, and then they'll take the difference, or the difference in pressure, difference in volume, and add it. And that's where this comes from. And they could build up the tables from that kind of data. If you come up to 100 degrees C, it says it's 101.42 kilopascals. That's boiling temperature, that's atmospheric pressure. And why is that? At this pressure, that's the saturation temperature. That's a saturation pressure for it. This has expanded. It's units of meters cubed per kilogram. There's more meters cubed for every kilogram. It's gone up 4% bigger. The water itself has expanded 4% in getting up to boiling temperature. By the way, 0.001 meters cubed per kilogram. What if we want to know the density? What are our units of density? It's kilograms per meter cubed. What if you have 0.001 and you turn it upside down? Yeah, and it ends up being 1,000. So there's 1,000 kilograms in a cubic meter of water at ice water temperature. But if you turn one of these upside down, it's going to be 4% less, so it's going to be like 960 kilograms per cubic meter, which is 4% difference. So these are just inverse of density. But we like to, in thermal, we're going to use not density, but specific volume, because everything's per kilogram, and we can scale it. So instead of kilograms per cubic meter, we'd rather have cubic meters per kilogram, because then our units are all, we don't have to take, it's always per kilogram, and we can scale it up when we want to know, how much energy do I get out of a kilogram going through this process? Okay, we get 317 watts. Okay, I need a 500 megawatt power station. How many kilograms need to circulate through it? And, that's, if we do it per kilogram, then it's easy to scale up. So all our properties are going to be like that. We'll be using these properties This is going to be a little bit later. This is about not the quantity of energy, but the quality of it. Essentially, how useful is it for us? This is a weird little concept, and we'll get there. So don't have to worry about that one right now. If you recall, there's different things in the tables: temperature, pressure. If you know temperature and pressure, then the internal energy follows, the specific volume follows. The pressure and specific volume added to this give you the enthalpy. Those are all going to follow, and it's for the liquid or for the vapor. Either case, there's information on that.
Is that what you just said, the multiplying? That is the multiplying that you just did across?
Yeah, and it's not always going to just work out. That's where it comes from, but if you try and just multiply the tables, you're probably going to get frustrated because it won't just match.
There's so many significant digits.
There's some other stuff going on.
Okay.
But if you know any two of these things, and the third thing you need to know is what is the pure substance you're using: water, refrigerant, oxygen, air, whatever it is. When you know what you're dealing with, and you know two properties, and you basically all the rest of it will fill in. So
if it's a different table, because this table is for saturated water. So if it's another substance, then it'll be a different table.
Different
but
table,
the same thing applies?
same concept.
Okay.
We're going to go through here shortly water and R134. And that's the thing about a state. If you have a pressure and a temperature, or a pressure and a volume, or a temperature and a volume, or an enthalpy and a volume, there's only one temperature, pressure, internal energy. All the rest of them can only exist. They're all, if you know two of them, then you can unlock the rest of them. And that's what the homework has some tables to that effect. I give you two things and tell me the rest. So we're going to go through that very shortly. This enthalpy, they're just adding internal energy. It's literally the internal energy, kinetic energy of the molecular motion, plus pressure times a specific volume, which is pressure times volume is work. So it literally did have some work that in expanding it, or if you compress it, pressure goes up, or maybe it doesn't go up, maybe it cools down and it's pulling it in, and there's less, you got work out of it. Enthalpy is your friend. We're not even going to worry about internal energy much at all. We're going to be using enthalpy to find out what's the total energy due to this pressure and temperature and all the energy that went into it with both heat and with work. So there's two columns that are of interest in there also. There's a F column, that's for a fluid, think liquid. And there's a G column that is for the vapor, the gas. So I think of the fluid, gas, F and G, it's liquid and vapor. And in the column,
It has three, H of F.
yep, and there's one
of
more thing
H
in there.
and one for F, H of FG.
Yep. So for our enthalpy, this is a property, and that's a property. And in between them is, this says HFG, also UFG, but this is built into enthalpy, that's why we don't have to worry about it. This is how much energy is in the saturated liquid that's about to turn into vapor. This is how much energy is in the vapor that's right ready to turn into liquid form again. And if you subtract this value from that value, that tells you how much energy it took to launch it's all at the same temperature. This is, you brought the boiling water up to 100 degrees. And now you have to add more energy to launch so that it goes, some of the molecules are going to come up and they're going to turn into vapor. That latent heat, it's how much energy does it take? This is how much energy it takes. And all they did was they know what this is a property of the vapor, this is a property of the liquid, and in between we're subtracting the difference. You need this much latent heat to turn it into vapor. This is we talked about latent heat numbers. This is it. But the interesting thing from this is you can see at ice water it takes 2,500 kilojoules per kilogram to take ice water, turn it into vapor at ice water temperatures at this really, really low pressure. It's still at that temperature, but it takes a bunch of energy to bust them loose. Because everything's going so slow, it has to like speed it up. And that's, you know, sublimation is probably that kind of number when it ice. You'll see ice on the sidewalks here in January, and then it stays cold enough overnight and during the day. It doesn't melt, it just suddenly goes away, and the sun will come and it'll actually launch, you know, that much energy will launch a molecule, and it just sort of works its way down. This column gets smaller as the temperature increases because the molecules themselves are shaking, the liquid molecules are shaking more, and so it's easier to come loose, maybe, that's how I think of it. But this goes, and when it comes to the critical point, which is in the next page, that goes to 0 and you stop having a steam table because it's not steam anymore. So that's, because we can't call it a liquid phase change. You get smaller and smaller and smaller, and when finally you get up to the 373.95 degrees at 22 megapascals, that's the critical point. There's no phase change going on. Everything's moving so fast that it's overwhelming the surface tension, and it just doesn't. It's not something we have an intuitive sense of. So that's where the table stops. But that's not the only table. Oh, by the way, there's 2 ways the tables go. You have a temperature table. The temperature table is 5, 10, 15, 20, 25, 30. Anybody notice a trend here? Notice a trend here? No. But if you have this temperature and this pressure, then you add, then you're into the phase change zone at that temperature. You can use this, for instance, say I want to cool down my lettuce. I've got a truckload of lettuce that I need to ship, and just got it out of the field. It was an 80-degree day. I washed the lettuce, put it in a box, and I want to chill it down to 15 degrees C or 10 degrees C. If I pull this vacuum, the water's going to evaporate down to that temperature and no lower. And as long as I can keep pulling, maintaining that vacuum, I can measure that vacuum, and I will know that if I give it a minute, the head of the lettuce, the very center of the lettuce, on the outside it'll evaporate and it'll be 10 degrees. The head might still be warm, but that vacuum is going to pull the moisture out of the middle, and when it gets to the point, it's going to pull the heat out of it faster than it could conduct if you put it in the refrigerator. So you can actually use these properties to flash cool a vegetable like that, and they do. That's done in industry without the danger of freezing. Anyone freeze lettuce? It's not really good after you freeze it. That's why they don't sell frozen lettuce. It just turns into like cooked spaghetti.
How do they do the vacuum thing?
Big chamber,
Okay.
and the pictures I've seen would be like pallets, and they'd load like 3 or 4 or 5 or 8 pallets,
Okay.
in as little space as possible because they don't want to, And then I'm not entirely. They have a rough suction thing that pulls it down,
Kind of like you can,
high volume,
like
and then
industrial one of those you can have at home and to do with your meat and
kind of,
suck it. Okay.
kind of, yeah. It's just industrial scale. Sure. So there's a temperature table, but there's pressures that go with that. Sometimes what you know is pressure. So the next page, table A5 in this case for water in the metric side. What do you know about the pressures? See a trend? They'll skip around, but they're definitely, these are round numbers. Do you notice a trend on the temperatures? But these correlate, and they're just interleaved. They're the properties. Just in one case, you know, if you go through by temperatures, you get a bunch of oddball pressures. If you go by the pressures, they kind of fit in between. And if you have a known pressure, you probably want to look on the pressure table. If you have a known temperature, you want to look on the temperature table. Can you find it, the pressure one on the temperature table? Yeah, but it's like you got to split hairs and do interpolations. So just to let you know, they already did a couple things for you. They gave you a temperature and a pressure table that are both saying the same thing, but they've lined them up differently. And they've already done subtracting the difference between these two, because you'll find this is commonly a piece of data you need. And all they did was do that calculation for you ahead of time. Another table. You're saying to yourself, these tables are so good, how could it possibly get better? Well, here's how. All of those tables, I'm wondering if I should just bring that over here. Let's see if I can get it. Over here on the wall, we have a chart. This is all the tables in one picture. Oh, well, that's not working. And this chart's in the back of your book, but formatted differently. This is the saturation dome, and all of these charts are just taking data underneath and on the edges of this dome. There's lines here that kind of swoop up. Those are enthalpy lines, and you can predict all these properties off of this. But the problem is these tables don't deal with all of this area here. This is the superheated steam. Here's liquid, you heat it up, it comes across, and now it's vapor, and now you heat up the vapor. You're going to have to deal with that zone of superheated vapor. So we need a different set of tables. And that's what the superheat tables are about. What happens if your vapor is beyond saturation? If it's not just your teapot, but you heated it up in the teapot and then heated it up some more. So each one of these is a certain pressure. And at that pressure, they have a table of temperatures. And based on, and they're in megapascals. So for instance, what is, let's look at this one here. 0.1 megapascals. What's that in kilopascals? It's 100 kilopascals, close to atmospheric temperature or pressure at standard pressure, which is really 101 point something. But this is 100 exactly. That's the saturation temperature. If you don't believe me, look at the pressure table under 100 kilopascals and then say that number. And it will also say the first line here, I believe, is the saturation values for the vapor. If you look on the table at saturation, the pressure table, you should find entropy, which we're not using yet, enthalpy, which is our favorite one, internal energy, which you really don't use much because it's built into that one, and you'll find the volume. This is the vapor volume. So what this is saying is 1.69, almost 1.7 cubic meters for a kilogram of steam at boiling temperature. And if you have a different pressure, they put in the saturation value, and then they have all these different temperatures. So we're going to use this. And so specific volume, enthalpy, internal energy, entropy, which we won't be using that for another chapter or two, but if it's F, it's a liquid, if it's G, it's gas. FG means the difference between how much energy it takes to go from one to the other or vice versa. There's also a table for ice that you have that we haven't used much, but I think they use FG and I don't think they use I, L or something. Anyway, the amount of energy it takes and different pressures and it's after these tables. There's an ice table. I'll flip to that in a minute. When we talked about latent heat before, the heat capacity, that's really this HFG, how much it takes to go from liquid to vapor. And HFG is 0 at the critical point. That's what we were just talking about when it gets, there's no phase change when you get to that super high temperature, super high pressure. Yeah, we'll talk through this. Here's another property. If you're somewhere between saturated liquid and saturated vapor, you have to define where you are. Did half of the mass melt into, or of the liquid turn into a vapor? Or is it 3%, or is it 90%? That tells you how much energy you put in there by mass. So there's this thing called quality that has to do with when you're underneath that saturation dome, a certain amount of energy. You didn't have as much, didn't put as much energy into it as it took to vaporize it all. You want to know maybe how much more is it going to take? You want to know what's that state? And it's going to have to do with mass of the vapor divided mass total, mass of the fluid, and since everything is in terms of kilojoules, kilograms, you can find that by interpolating between the liquid and the vapor. Just like we did for finding the temperature for the pressure point. Do we have a formula for that? So if you know a certain volume, specific volume, the X is going to be the difference. What is the what volume do you have? Minus what would the fluid volume be? If it's bigger than the fluid volume, if you had a relative to how far could it go to be all vapor? If all of the mass turned to vapor, this number would be the same as that number, because the volume of the, oh, that's backwards. It should be gas minus, no, this is backwards. That needs to be flipped. You can either use this information to find an actual volume, or you can use, find the quality, how much of the liquid vapor mixture is liquid, how much of it is vapor. We're going to be using this term, and mostly we're going to be using for volume, specific volume, and enthalpy. And usually what happens is we know what a volume is, and we use this to find the quality, and then we use the quality here to find the energy. We can measure the volume. And by measuring the volume, if we know what the mass was and measure the volume, then we can use the formulas and the tables to backtrack into how much energy is in a container, which will be more relevant when we're talking about a boiler and a steam turbine. That's where that comes from. And I'm going to, that is bad karma right there. If you have notes, feel free to make that change. The volume of the gas is always bigger than the volume of the liquid. So that quality problem is important. And here's a hint for if you get into the superheated vapor region, the volume is likely to be bigger. We'll get to this. A couple of ways you can recognize whether it's superheated vapor. It's probably best to just go through some examples here. It gets kind of confusing. So here's an example. We're looking at R134, and what we know is, okay, we're talking metric table, so we're in the first appendix. The first line, we know it's 8 degrees, negative 8 degrees centigrade, and had a pressure of 500 kilopascals. And based on this, what do I know? I could look either the volume or the pressure table because those are round numbers. Both of them are round numbers.
What's the last one after volume?
Phase. Is it saturated liquid?
Okay.
Is it saturated vapor? Is it a mixture of the two? Is it superheated? Is it just liquid, not saturated? Those are kind of, it can either just be a liquid or it got heated up to its saturation temperature. It can have been converted, or it could be in between those two. Or it could be beyond the vapor thing. So I'm going to look on the pressure table for 500 and find what it tells me about negative 8. So at
What page is this?
this page is 994, table A12.
Okay.
And when I look at 500 kilopascals, it says the saturation temperature is 15.7 degrees C. 500 kilopascals, 15.7. I'm below that temperature. So it's not a solid, it's a liquid. It's going to be a liquid. So, and it's not a saturated liquid because it's below its saturation temperature. It's below where it starts. So it heated up and then it'll start boiling. So that being the case, what I know is it's a, can call it subcooled liquid, or you can call it compressed liquid. I'm going to call it compressed liquid, but basically it's cooler.
So it's still,
And we still
so
don't
it's
know.
still liquid,
It's definitely a liquid. It's not close to boiling.
but it's not a saturated liquid.
It's not saturated.
So how do we get-
So, whoops, where did it go? So the next question is, how do we figure out what the volume is? Now here's one of the tricks, and that is we don't have a table for liquid subcooled. But once you have a liquid, it doesn't really matter how much pressure you put on it. It's a little squishy, but not much at all. So but it expands with temperature, just like you know, pipes in your house. If it turns into ice, it will break the steel. It just does. It's going to expand. It will expand one way or the other. It will expand, and temperature is more important. That question?
When I look up -8 on the temperature,
Right.
I go over to the saturated pressure in kPa, and it says 217.
Right. So if this was lower pressure, it could add some energy. It would boil. But we put more pressure on it. It's like a pressure cooker, so it's not close to boiling. So I like that though. So that's why I call it compressed liquid. It has more pressure than it needs for boiling temperature, or for the boiling.
But it doesn't have the temperature.
But this doesn't match, but we are going to use that data because it turns out that the temperature is what matters for the size when it's a liquid. So what does your table say for the specific volume?
It only has saturated, everything says saturated.
Yes, it's going to be the same. We're going to use the same volume.
So it's 0.00075771?
Yep.
Okay.
Because the pressure doesn't really change the size of it. So here's -8, and if we let off some of the pressure, if this went down to 200, and we let off enough pressure so it went down to this space, 2 atmospheres, 15 psi. These are absolute, by the way.
Question though.
So if we drop it down to 200, which would be like 2 atmospheres, which gauge pressure would be like 15 psi, it would start vaporizing, and it would vaporize until it got down to -10 degrees. It would cool off if we let that go.
So,
it would boil a certain amount.
I'm looking at the table right now, right? The
Right.
-8, and it does say 0.007571
Right.
for the saturated liquid
Right.
VF.
Right.
Now, if we look at the previous table,
Right.
under the 500 pressure,
Right.
for the same saturated liquid volume,
Right.
it's a different number.
Right. And it's warmer.
Now, how do we know which one to use? Do
You
we
want
use
the
one-
temperature and pressure together.
So that one is 0.008059.
8059. Now that would be if it warmed up.
Okay.
If this goes down to -8.
Okay, so the volume is dependent on the temperature.
of the
Okay,
liquid.
that's what. That's the
Because the
catch.
liquid, that's why they use liquids in your brake
That's the
system.
catch.
They
Okay.
don't they're not squishy. They're almost like steel as far as, I mean, and fluids will go through the compressibility of liquids, and it's like 75, it's like way more like steel than it is like a gas. They do compress, yes. For our purposes, we're not going to deal with it. But if you
Okay.
come in here and came down to the temperature, you'd be in that ballpark of this 7, whatever it was. There's -8 would be between those two. So that's one. Let's try another one. 30 degrees C,
Right. Saturated,
and we don't know yet. 30 degrees C, and 0.022 specific volume.
Yeah, I did find that.
So
If I look at the 30 on the table, I'm looking 993. Is that the one you're at? I see 0.26622.
here we have
Yeah,
30 degrees.
Yep. We have 0.2.
And we're looking for 0.22. By golly, we don't have 0.22. We have 0.008, 0008, and 0.026622. We're somewhere in between. That means we're in the saturation zone. Bingo, we know the pressure. The only way it could be that volume is if some of it boiled off, but not all of it, which means that they're both liquid and vapor in this enclosed container. And the only way it can be that way at that temperature is if it's a mixture at that temperature. It has to be at saturation pressure. So we now know the pressure. And so, what else do we know? It's saturated. It's not big enough to be all vapor. It's not small enough to be all liquid. So it's what you call a saturated mixture. And if we wanted to, we could find out what that quality was.
Do you use that saturated pressure there? That's listed there, the
Yes.
770?
Yep.
Okay.
And how do we find the quality? I'll run through this quality. What we have is 0.022 and minus 0.0008. Oops. 0.0008, 421. Divide that by 0.026622. minus 0.00084421. This would be the entire range. This is how far we went in that range. This is my specific volume actual minus specific volume of the liquid over specific volume of the vapor minus specific volume of the fluid. And you come up with what proportion of it has turned into vapor, mass of vapor. Because if it had gone all the way to the full-on value, it would be 100% vapor.
Is this something we're gonna have to do?
I'm going to go to the next one. It's if anyone happens to have that number cranked, that's good. Otherwise, we're just going to move to the next one. That's how we get there.
What would that number give us?
That tells you the mass percent of the kilogram that is vapor by mass. Because if this value went all the way up to this value, you'd have this would be 1, and if that's the case, then it'd be vapor. Yeah. Let's do one more here on this one. 320 kilopascals and saturated vapor. So 320 kilopascals is here. We know it's in the saturation table, and we can just read off the data. There's temperature, there's that's the pressure, there's the temperature, and saturated vapor means we're
Which
looking
one are you
at
doing now?
that's the next one.
10 and then 600. You went to the pressure.
So I went to the pressure table, and at 320,
320.
it says the temperature is
What you have to go to
2.46.
600?
See?
320 here. Okay, so
And
320.
volume for saturated vapor is
0.046.
0.063604.
Yeah, 246. So he did use 3.46. And then the volume 0.06364. Then the next one is a 600. 600. So the volume
Next.
is 0.034295.
Next one's 600 kilopascals at 100 degrees C, and here on the table it says 600.
The volume 0.034295.
Well, no, hang on. 600 kilopascals, last one, and the saturation temperature is this much, but the temperature is actually 100 degrees C.
Way higher.
That means we're into the superheat table because it's higher than the saturation temperature. We don't have to worry about whether it's liquid or vapor. It's all vapor, and we heated it up. So that's how the tables work. We'll do this again tomorrow.
Can you do the last one tomorrow? So we can
Yeah.
separate it. Okay. I was thinking it would be super easy.